Hello and welcome back. In the last video we discussed about the OSI model, and we also talked about the TCP/IP model, and we also saw the differences between the two models. In this video we're going to talk about layer 2 concepts. We're going to start by looking at Ethernet, which is a layer 2 technology. We'll then talk about MAC addresses. We'll understand the differences between collision domains and broadcast domains. We'll also talk about VLANs or virtual LANs. We'll understand how it is such an important technology at layer 2. We'll talk about spanning tree protocol, and we'll understand how it is used to prevent layer 2 loops. We'll then talk a little bit about network devices, and finally we'll touch a little bit upon optical networks. That's the plan for this video. Let's begin. I know a lot of people who know about Ethernet, but when you go and ask them, what do you mean by Ethernet? They don't have an exact answer to that question. They know Ethernet, but they're not able to tell you what Ethernet is. So let me put this in simple terms for you. Ethernet is a set of technologies or protocols that define communication at layer 2. That's as simple as that. Ethernet is just a set of technologies or protocols that is used to define the communication at layer 2. Ethernet was originally developed by a company called as Xerox, and it was later on standardized as IEEE 802.3. So you may hear IEEE 802.3 and Ethernet, both these terms being used interchangeably. Both of these actually refer to the same thing. The most important thing about Ethernet is the Ethernet frame format. We discussed earlier that at layer 1 of the OSI model, what we have is data in the form of bits, which is nothing but ones and zeros. But when this data actually moves to layer 2, it gets converted into what is known as frames. So what happens to these ones and zeros that convert them from bits to frames? So all these headers that you see here, these headers actually get added on top of these ones and zeros to convert these bits into frames. Let's talk about these headers for a minute. The Ethernet frame format starts with 7 bytes of preamble. The preamble is 7 bytes of alternating ones and zeros. So this is how the preamble would look like: 10, 10, 10, 10. So that's 1 byte of alternating ones and zeros. And then one more time, 10, 10, 10, 10. That's 2 bytes. So you would have these 7 times to make a total of 7 bytes of alternating ones and zeros. The preamble is used by the source and the destination to synchronize their internal clocks. That's what the preamble is used for. After the 7 bytes of the preamble, you have 1 byte of SFD, which stands for Start Frame Delimiter. The SFD would look like 10, 10, 10, and then 11. The SFD is used to indicate the end of the preamble. That's what the SFD's function is. Okay. After the SFD, we have 6 bytes of destination MAC address. We then have 6 bytes of source MAC address, followed by the 2 bytes of length. This field is used to indicate the length of the payload that's going to follow. And then we have the actual payload or the data, which could be anywhere between 46 to 1500 bytes. After data, we have some padding, which means if your data or your payload is less than 46 bytes, we add some padding to make it a minimum of 46 bytes. And then finally, we have 4 bytes of FCS, which stands for Frame Check Sequence. It is used to make sure that the frame has not been damaged in transit. So here's how it works. It takes 4 values: destination MAC address, source MAC address, length, and the payload. All these 4 values are used to compute a new value called as CRC, which stands for Cyclic Redundancy Check. It's also known as a CRC value. This value is calculated at the source and at the destination to make sure that the frame has not been damaged in transit. That's how an Ethernet frame format looks like. Okay, let's now talk about CSMACD. Before we begin talking about CSMACD, I do want to point out, just in case you're curious, Ethernet is not the only technology that defines communication at layer 2. We have other technologies as well, like token ring. However, this is not used nowadays. We also have something called as FDDI, which stands for Fiber Distributed Data Interface. We also have something called as ATM. So there's multiple technologies that define communication at layer 2. However, Ethernet happens to be the most popular among all of these. Alright, let's now talk about CSMACD. So CSMACD stands for Carrier Sense Multiple Access with collision detection. Now, by the way it sounds, you feel that it's very technical, but let me tell you, it is not. It's just a very simple concept used to avoid collisions over Ethernet. Okay, so here's how it works. Let's say we have a shared medium and we have two computers here. It's computer A and this computer B. Both of them are connected to a shared medium. Now, when any of these wants to send data over the shared medium, they're going to first check to make sure that the medium is free. So the first thing to make sure is that the medium is free. After that, once it is determined that the medium is free, one of them can start sending the data. But what happens if both of them send data at the same time? That results in what is known as a collision. When two devices try to send data at the same time, that's what is known as a collision. Now, when a collision happens, both these devices are going to send what is known as a jam signal and then back off for a random amount of time. So it could be some X seconds. So they'll back off for a random amount of time before they begin to retransmit their data. That's all about CSMACD. And remember, we are talking about half duplex communication here. CSMACD applies to half duplex communication. So let's repeat the steps one more time. There's a shared medium. Any node that wants to transmit data will first check to see that the medium is free. If the medium is free, it will then begin transmitting. However, if two nodes try to transmit data at the same time, it results in what is known as a collision. Once a collision is detected, both the nodes will send what is known as a jam signal and then back off and wait for a random amount of time before they begin to retransmit. That's how CSMACD helps in avoiding collisions. MAC address is the physical address of a computer. It's the physical address of a computer, and it is the address that is burned into the chip of the equipment. That's why we call it as a physical address. MAC address is a 48-bit address represented by 12 hexadecimal characters. As you can see, 12 hexadecimal characters. These hexadecimal characters are divided in groups of 2. So you have 6 groups of 2 hexadecimal characters. Every hexadecimal character can be represented by 4 binary bits. So you have 12 characters, 4 into 12 makes a total of 48 bits. That's why it is a 48-bit address. Also, it is written in hexadecimal format. Out of the 6 groups of hexadecimal characters, the first 3 groups combined is called as the OUI. It's also known as the Organizational Unit Identifier. The OUI is used to identify the manufacturer of the network equipment. So these 3 groups will help you identify who manufactured the network equipment. It's also called as OUI. Now, there's 2 special kinds of MAC addresses that we need to talk about. Number 1 is the broadcast MAC address. A broadcast MAC address is made up of all Fs. So like the characters that you see here, you put all Fs and what you get is a broadcast MAC address. Excuse my really horrible handwriting. I have that listed here. That's how a broadcast MAC address would look like. If we convert this into binary, it would be all ones. Any frame that is sent with the destination MAC address as the broadcast MAC address would reach all the hosts on that network, okay, because it is a broadcast MAC address. The other special MAC address that we need to talk about is the multicast MAC address. The first 24 bits of the multicast MAC address is reserved as 01005E. Remember, every hexadecimal character can be represented by 4 binary bits. So you have 6 characters, which makes the first 24 characters. So the first 24 bits, as you can see here in binary, is fixed, and in hexadecimal it would look like 01005E. The interesting part is the 25th bit is also fixed, and it has to be a 0. So the first 25 bits of a multicast MAC address are fixed. The lowest possible multicast MAC address would be when you fill all of these with zeros, you'd get 000000. That's the lowest possible multicast MAC address. The highest possible multicast MAC address would be when you fill all of these with ones. So the first 4 bits would give you a 7, and then the next 4 will give you an F because it is all ones, and the remaining also happens to be ones, so you'll get this. That is the range of a multicast MAC address. That's about MAC addresses. Let's now talk about collision domains and broadcast domains. Collision domains versus broadcast domains. If you look at the networking definition for collision domain, you're going to get highly confused. If you don't believe me, go ahead and check the networking definition for collision domains. It's really confusing, but I'm going to put it in a very simple way for you. To understand collision domains, just think of this. How many devices can send data at any time? That is what defines collision domains. So let's say we have a hub here, and that's a 4-port hub. How many devices do you think can send data at the same time? The answer is only 1. So that is one collision domain. Let's look at a switch or a bridge. So we have a switch here. Let's say the switch is also, or let's say the switch is an 8-port switch. How many devices do you think can send data at the same time? The answer is all these devices can send data at the same time. In this case, there are 8 ports, so there's 8 collision domains. If it was a 16-port switch, that's going to be 16 collision domains. What about a router? So let's say we have a router here, and it's a 2-port router. In this case as well, both devices can send data at the same time, so it's 2 collision domains. So remember this, my friend, a hub is one collision domain because only one device can send data at the same time. A bridge or a switch is different. The collision domains equals the number of ports because every port is able to send data at the same time. And the same logic applies to routers as well. Alright, let's talk about broadcast domains. Now again, if you read the networking definition for broadcast domains, it might not make too much of sense to you. So let's put it this way. Let's talk about a switch for a moment. And let's say it's an 8-port switch. If any one node connected to any of these ports sends a broadcast, how far do you think this broadcast is going to reach? Well, the answer is it's going to reach all these devices on the switch. So it is a single broadcast domain. There's only one domain on which you can forward the broadcast. The same applies to a hub as well. Let's say it's a 4-port hub. If a device sends a broadcast, it's going to reach everybody on that hub. So it's one broadcast domain. Let's talk about a router. So let's say it's a 2-port router. Let's say the node that is connected to this port sends a broadcast. Do you think the broadcast is actually going to travel across the router? No, because a router cuts a broadcast. So the broadcast can only reach so far. In the same way, if a broadcast comes from this direction, it's not going to cross this port here. So that's 1 plus 1, a total of 2 broadcast domains. So on a router, the number of broadcast domains would be the number of ports. On a switch and a hub, it's only 1 broadcast domain. Remember this, my friend. Let's now move to the next topic. VLANs or virtual LANs. We just discussed about broadcast domain, and we saw how a switch is a single broadcast domain. What that means is any device that is connected to the switch, when it sends a broadcast, the broadcast reaches all other devices on that switch. Now if that switch is a small size switch like a 8 port or a 16 port switch, that's fine. But think about the bigger switches like the 48 port switch and the 24 port switch. Imagine a device sending a broadcast reaching all other ports. Devices tend to send broadcasts periodically, so every now and then some device is actually trying to send a broadcast and every other device is actually receiving that device. Imagine how much of a menace that would be on higher end switches like a 48 port switch. That's not good. Too much of broadcast traffic is never good. Also think about this. So let's say we have a college local area network. Imagine we wanted to divide this LAN into two parts, one for the professors and one for the students. How could we do that? Also think about this. Let's say we have a mixed traffic environment. So we have data traffic and we have voice traffic. And we want to prioritize voice traffic over data traffic. How would we do that? How would we apply different policies and quality of service for the voice traffic? The answers to all these questions is with VLANs. VLANs also stand for virtual LANs. A VLAN is a logical separation of a layer 2 segment or a switch. So you have the switch here. A VLAN will allow you to divide the switch into multiple parts. That's the power of a VLAN. Imagine how flexible this would make your network. So once you divide your network, you are then able to separate data traffic from voice traffic. So now you can apply quality of service. You can divide your LAN segment into two different parts, maybe for different people. Maybe a college environment, so you have professors and students. You divide the same LAN into two different parts. You can now control broadcast traffic because once you divide the switch into smaller parts, broadcast traffic is going to start reducing. It's not going to reach all the devices. So you can understand the power of virtual LANs or VLANs. Before we go further, let me clear the board. So I'm going to draw a switch again, which has been divided into two parts with the help of a VLAN. It is important to remember that every VLAN is a different network. So if this one is 192.168.1.0, this could be 192.168.2.0, 2.0/24. So every VLAN is a different network in itself. By default, these VLANs will not talk to each other. To make them talk, you need to introduce a layer 3 device like a router. Only then you can make these two networks talk to each other. Also now, since you've separated the networks, you can now apply different policies to different networks. If you're wondering how many VLANs can you create on a switch, that would depend on the model of your switch. The higher end switches may allow you to have more number of VLANs compared to the lower end models. How do you identify VLANs? So let's say we have two VLANs now. How do we identify these two VLANs? We identify VLANs using VLAN IDs. The range for VLAN IDs is 0 to 4095. So you could have VLAN 0 all the way up to VLAN 4095. However, it is important to remember that VLAN 0 and VLAN 4095 are reserved, which means you cannot use it for production traffic. All the other numbers inside this range is valid. Next question, how do you identify that a packet actually belongs to a VLAN? So any packet that is generated on a VLAN has two fields in it. Number one is the TP ID field, which stands for tag. It stands for tag protocol identifier. So any packet that is generated on a VLAN will have the TP ID value set to 0x8100. That's the hexadecimal value for the TP ID field if the packet has been generated on a VLAN. The second field is the VLAN ID field, which will be the values from 1 to 4094, indicating the ID of the VLAN. If your switch has not been divided into VLANs, the packets are considered to be belonging to the default tag, and the packets are called as untagged packets, meaning they don't have a tag for a VLAN. So that's about VLANs. Let's now move to the next topic. Layer 2 loops and spanning tree protocol. Now before we start talking about spanning tree protocol and why it is so important, let's understand layer 2 loops for a second. So layer 2 loops are both good and bad at the same time. Let's understand how. So you see this diagram here, we have three switches, switch A, switch B, and switch C. And as you can see, all of these switches are interconnected, which means there's a loop in this network. What that means is, if any of these three links actually goes down, let's assume this link just went down, switch A is directly able to reach switch C, and it is also able to reach switch B via switch C. So in that way, layer 2 loops are good. They give you redundancy. But think of this for a moment. Let's assume apart from these two ports here, switch A also has an additional port on which it receives a broadcast. By default, a switch will always forward a broadcast on all other ports other than the one on which it received the broadcast. So switch A received a broadcast on this port, it will forward the broadcast on this port and this port. Now switch B received the broadcast from switch A, and that broadcast will be forwarded on this port. Switch C will forward the broadcast received from switch A on this port. Now the broadcast that switch B sent to switch C, it was received on this port and it will be forwarded on this port. The broadcast that switch B received from switch C was on this port, and now it will forward it out this port. Did you notice what just happened? The broadcast that was sent by switch A has returned to it. And this is not going to stop. This is going to go on forever. This will result in a broadcast storm, and it will consume all resources of your network. That's why layer 2 loops are bad as well. It introduces broadcast storm and it consumes your important resources. That's where spanning tree protocol comes into play. Let's understand how spanning tree protocol efficiently controls loops at layer 2. Okay, so spanning tree protocol begins by electing what is known as a root bridge. Now when we use the word bridge, we also mean switches. So spanning tree protocol begins by electing a root bridge. Think of the root bridge as the central switch of the network. It is the switch from whose perspective you're going to view your network. That's what the root bridge is. To elect the root bridge, we need something known as bridge ID. The bridge ID is a combination of MAC address plus priority. These two values combined give you the bridge ID. The bridge priority is a user configurable value on a switch. For the EX series switches, this value is 32768 by default. Now for the simplicity of this example, let's just assume all switches here have a default priority of 4096. Okay, all switches have the same priority. Now the bridge ID only depends on the MAC address. The switch with the lowest bridge ID gets elected as the root bridge. Now since the priority is the same, it only depends on the MAC address. So the bridge with the lowest MAC address would become the bridge ID. And just in case if you're wondering how this combination would look, it's simple. So just take the MAC address for switch A, which is 11111111, and then you put the priority. It gives you a numerical value. So the lowest bridge ID becomes the root bridge. In this case, the lowest MAC address happens to be with switch A. So switch A will be elected as the root bridge. Once the root bridge has been elected, the root bridge will put all its ports into forwarding state. So in this case, switch A has two ports. Both these ports will be in forwarding state, which means it will pass traffic. All other switches other than the root bridge will calculate the best way to reach the root bridge. So for switch B, the best way to reach switch A is through this port, and for switch C, the best way to reach switch A is through this port. So all other switches other than the root bridge will calculate the best way to reach the root bridge and put that port into forwarding state. So this port for switch B will be in forwarding state, and this port for switch C will be in forwarding state. All other ports to reach the root bridge will be put in blocking state. For switch B, this happens to be the other way to reach switch A or the root bridge, so this will be disabled or put in blocking mode. For switch C, it's this one that will go into blocking mode. So what's happened here is the loop has been removed. That's how spanning tree protocol controls loops at layer 2. So what happens if any of these two links actually go down? So let's say this link just went down. These two ports are now going to be activated by spanning tree protocol. So this starts forwarding traffic and this starts forwarding traffic. So switch A can still reach switch B, and it can also reach switch C via switch B. You see how important spanning tree protocol is at layer 2. Now if you've been very impressed with spanning tree protocol and you've decided to turn it on your switch, don't worry my friend, it is already turned on all switches. That's about layer 2 loops and spanning tree protocol. Let's now talk about network devices. Network devices can be classified mainly into 5 types: repeaters, hubs, bridges, switches, and routers. Those are the major classifications. Let's first look at repeaters. A repeater is a layer 1 device, and just as the name sounds, it is used to repeat signals. It just repeats the signals. The important thing to remember here is that a repeater does not amplify your signals. It does not amplify signals, it only repeats the signals. On the other hand, a hub is a layer 1 device that operates in half duplex mode. So you can have multiple ports for input and output. Data that is received on one port is forwarded out on all other ports. A hub does not have any intelligence of its own, which means it does not learn MAC addresses. And hubs are not good from a security standpoint because any data that comes in is forwarded out all the other ports, so everyone gets a copy of the data. So hubs are not good from a security standpoint. Let's talk about a bridge. A bridge is a layer 2 device which operates in half duplex mode. The interesting thing is that the bridge has the capacity to learn MAC addresses. It learns MAC addresses. So the first time the bridge receives a frame, it is going to remember the source MAC address and the port into its CAM table, and then it is going to forward the frame out all other ports. The reason is because it does not know where the destination is located. Once the destination replies, it is then going to add the destination MAC address and the port into its CAM table. So the next time the bridge receives a frame for this destination, it's going to forward that only out that port. And frame forwarding on a bridge is software based forwarding. Excuse my handwriting, I know it's really bad. So a bridge does software based frame forwarding. Let's talk about a switch. A switch is also a layer 2 device. However, it operates in full duplex mode. It learns MAC addresses, meaning the first time it gets a frame, it is going to store the source MAC address and the port information in the CAM table and forward that packet out all other ports. Once the destination replies, it is going to save the destination MAC address and the port in the CAM table. So the next time it receives a frame for the same destination MAC address, it will forward that only out that port. Now on a bridge, frame forwarding was software based. On a switch, frame forwarding happens with specialized hardware known as ASICs. It stands for Application Specific Integrated Circuits. Don't worry, you don't have to remember that. Alright, so forwarding on a switch happens with specialized hardware known as ASICs, and the most important thing, switches support VLANs. A bridge does not support VLANs. So those are the differences between a bridge and a switch. A bridge works in half duplex, a switch works in full duplex. Frame forwarding on a bridge is software based, while frame forwarding on a switch is hardware based. There's ASICs that do frame forwarding. A bridge does not support VLANs, however a switch supports VLANs. A router is a layer 3 device, and like the name sounds, it does routing. So each port of a router is on a different network, so it routes the packets between the networks. And a router uses what is known as routing tables to store these different networks. As simple as that. So router, a layer 3 device that does routing. Every interface or every port of the router is on a different network, and it uses routing tables to forward traffic. Optical networks. Optical networks is not a very major topic. However, we do need to remember some important points from the examination standpoint. So let's talk about these points. Number one, traditional networks, traditional telecommunication networks have been laid out on copper cables. There's two major problems with copper cables. Number one is interference, also known as crosstalk. That's the first problem. The other one is bandwidth issues. When it comes to copper cables, we can only reach a certain amount of bandwidth. That's where fiber optics come into the picture. Fiber optics can provide bandwidth that is up to 1,000 times greater than what you get on traditional copper cables. Optical fiber networks have two components. Number one is the fiber itself, and number two is the laser beam that carries this data. Those are the two components of optical fiber networks. SONET stands for Synchronous Optical Networking, and this was designed or developed by ANSI, which is American National Standards Institute. SONET defines standards for communication such as transmission speed and coding schemes. These are some of the things that are defined by SONET. Now, SONET was designed by ANSI. Take SONET to the international level, and what you get is SDH, which is Synchronous Digital Hierarchy. So SONET designed by ANSI, on an international level it is known as SDH. Pretty much the same thing. The other topic that we need to discuss is DWDM. It stands for Dense Wavelength Division Multiplexing. It is a technique that is used to carry data from multiple sources onto a single fiber. The way this is done is by having different wavelengths for these different sources of data. So all these different sources of data have different wavelengths, and all of this is actually multiplexed onto a single fiber. That's what DWDM does. Optical Transport Network is a framework or protocol that adds extra features into carrier networks. What kind of features, if you ask? Things like framing conventions, error control, and performance monitoring. These kind of features are added by Optical Transport Network into carrier networks. That's what Optical Transport Network does. Those are the important points as far as optical networks are concerned. So in this video, we started by looking at Ethernet. We spoke about CSMACD. We spoke about MAC addresses, and we understood the differences between collision domains versus broadcast domains. We also discussed VLANs and spanning tree protocol. We understood network devices and optical networks. Lots of good things in this video. I'm really happy with the way we progressed in this video. In the next video, we are going to start by looking at a very interesting topic known as subnetting. I'm really excited to see you in the next video, and I'd like to thank you for watching.